Julita Corbalan.
Corbalan. Yes.
And Julita is a team leader of the system software for energy management in the HPC group at Barcelona Supercomputing Center. And the title of her presentation is, Could Energy Aware Runtime be the European bet for AI HPC Data Center energy optimization? Thank you very much, Julita.
Okay, so thank you for attending the presentation. I'm going to talk about a totally different topic and at the same time similar one, because I'm going to talk about energy optimization, okay? But in this case, I'm going to focus on a software solution or software approach to attack this problem, okay? So in this morning, for example, in the keynote, we have been listening about mostly hardware solutions or data center solutions, okay? My colleagues have been talking about other parts like the edge computing, FPGAs, and I will talk about a system software to address and to optimize as much as possible energy in data centers. So I think probably this slide is not really needed because all of you are aware that energy is an important topic, but let me just summarize the 3 main points we think in the EAR software project, what is the reason or our motivation to work on this important topic. So the first one, of course, is the money. We need to be, sorry, we get the other one. So of course we need to be effective from an operational point of view. So it's not only the matter of having a new system, a new machine, you need to be able to pay later the electricity. And this is a real, right now, is a very important problem. Second one, and also very important for all of us, is that we must be what is called eco-responsible. So the amount of resources we have is really limited. This morning, for example, I think it was in the Meta talk, not 100% sure, they have commented that data centers are consuming 3% or generating 3% of carbon footprint or something like that. So for a very small amount of, let's say, of the activity of the planet, is a big percentage of the carbon footprint. So in the EAR project, we want to contribute to that, and we want to help to be more energy efficiency. And it's a collateral contribution or an additional benefit to any other hardware or any other software solution. So what's EAR? EAR is a system software for energy management. Right now, for HPC AI data centers, our goal in the near future is to be more generic and not only addressing HPC or AI data centers. So what the EAR is offering is we like to say it's a global solution or more complete solution than other tools, because we offer system monitoring, is system energy and power monitoring, but this keyword of energy and power applies to everything on EAR, job accounting, job optimization, and also system optimization, okay? So of course we target energy and power because this is our initial motivation in the project, but right now mainly the part of monitoring is being extended to much more other metrics and information, basically performance, for the better understanding of why you are consuming or why you are consuming this power, this energy, or where you are using a given frequency. So these are the 3 main topics that we address in EAR, okay? So as you can see in the bottom, there are 2 parts that basically address monitoring, but from 2 different contexts. So on one side, we have a big effort in the part of the system monitoring. So from the point of view of the data center, they are really interested in knowing the power consumption, also in other metrics like temperature, frequencies, but also in the performance metric that the applications are collecting, okay? So on one side, we focus on system monitoring. So you can see in bold the 3 main keywords for this part. So we have an extensible monitoring system. It's compatible with other tools. I mean, we are complementary. We try to address different architectures, different devices, okay? The second part is that we have an extensible reporting system. Again, it's compatible with other things, but we are trying to be integrated as much as possible, integrated in the current trends in this part. For example, right now we have working in a reporting plugin, for example, for Prometheus. And finally, we are also providing an extensible dynamic mechanism that we call alerting mechanism, because in the data center, they want to be immediately informed about any issue with power or temperature, because that affects, of course, the whole infrastructure. On the other side, we have a powerful system for job monitoring. Okay, so there are two things here. So we are offering job accounting. Job accounting is the information for the metrics that in the data center they need to know, they need to store how much power, energy, every job executed in the system is consumed. This is what we call in ER basic monitoring. But on the other side, we are doing a runtime monitorization and characterization of what the jobs are doing, because we use this information for optimization. So all these metrics are also reported to our database. And in fact, it's something that from the data centers, they are requesting us more and more to add additional metrics, because something that we have clearly seen, there is a lack of understanding of the real workloads it's being executed in the data centers. On top of these two parts, we have a powerful job and system optimization. So what we call job optimization is basically the dynamic selection of the CPU, memory, and GPU frequency for the optimal execution of the job. Optimal depends on the criteria of the data center. There is not a single definition, but basically the data center gives us some reference, like they want to minimize energy, they want to accelerate only efficient jobs. So in here, basically, we have like two basic policies, but this is something, it's also extensible. At the cluster and the node level, we are also offering optimization, and in our case, optimization in that level means power cap. So ER offers node and cluster power cap. So let me do a little bit of zoom of what we do in terms of job optimization. So we have a ER runtime library. This runtime library is executed in the user context. And internally, it implements this kind of life cycle optimization process, which is executed again and again. So when a new application, new job starts, the ER library tries to identify if there is some repetitive pattern in the application. This repetitive pattern exists in many HPC applications, and there are a lot of research works using this characteristic, okay? Anyway, if the ER library detects that there is no these patterns, we switch automatically to what you see here, this time-guided. So we switch to a time-guided mode automatically, so we are able to deal with repetitive applications or not repetitive applications, okay? Anyway, when we detect this iterative behavior, we start computing what we call the runtime signature. Runtime signature is like a digital picture of what your application is doing right now. So with this runtime mechanism, we don't need any input, we don't need any external historic information, any user hint, we don't need any additional information. We can manage everything at runtime. So once we have the runtime signature compute, and I will show you later a set of metrics that are part of this runtime signature, then we compute an application classification. What is my application, my job doing right now in this phase of the execution, okay? So for some cases, like you can see here, for example, input-output of if my application is in a GPU bound phase or GPU idle period, or the CPU is doing a busy waiting, we have some specific predefined settings in terms of frequencies, okay? So in that case, we have something specific. If my application is in a typical computational phase, then the ER library applies some energy models and energy policies to select this optimal frequency. So the energy models use this runtime signature together with some coefficients that we compute when we install ER, and that we call system signature. There are no details here, but I can explain you something later because I will be doing a technical demo, okay? And in policies, basically, we have these two policies of these two criteria I have commented before. Or we minimize energy, or we accelerate applications, which at the end, if it's an efficient acceleration, it results also in a saving on energy, okay? All the metrics, all the signatures that we are collecting are being reported to the database, so you can do a post-mortem analysis, characterization of your application. I mean, any analysis, better understanding is up to you, okay? This internal loop is applied again and again at the runtime library, and the granularity, just to provide you a hint, the granularity of this signature computation is more or less 10 seconds, so we are not doing at the level of milliseconds, for example. Just as a hint, the set of metrics that are part of this runtime signature is, in terms of power metrics, we are reporting not power, but also the internals, the RAM, memory, GPU, for example, independent GPU metrics, okay? And all the metrics you can see here concerning power. So of course we report execution time, but we have metrics like CPI, cycle cost per instructions, memory bandwidth, the GPU activity, input, output, MPI activity. So it's a coarse characterization, coarse-grained characterization of the application, but that gives you a nice picture, enough detail of what your application is doing. So what are we doing at the level of the system? Because the previous slide was referring to the job optimization. At the level of the system, what you can see here is the ER architecture, okay? And a few hints, few ideas of how it's managed. Okay, so in here we have different components. I have been talking about the runtime library, but we also have the ER daemon. That is an ER service, a Linux service running on computational nodes. And then we have the global manager, which is this meta global manager and this one. So this is a hierarchical architecture. Depending on the cluster size, maybe only one of them is enough. But for very big clusters, we have decided this hierarchical architecture, where you can have multiple global managers taking care of partitions of or subclusters. And if it's needed, we can have one meta global manager doing a very coarse-grained power redistribution between partitions. So what is interesting on that is, first, is hierarchical architecture. Second is a stateless design. Okay, so you can stop, change the configuration, and start again. There is no problem. Okay, and the API is very, very simple and really extensible, because basically the communication in all the levels is very, very similar. It's something like get power, sending settings. So what we are working right now in here is a part of always trying to improve, support more use cases, and so on. We are trying to do something more, a little bit more for our customers with the information that we are gathering. So we are working in two sides. On one side, providing automatic reports on the workload characterization. So for example, we can compute graphs like this one, which is from a real system, where you can see the percentage of CPU time consumed per user. So for example, in this data center was a user consuming close to 50% of the total energy of the data center, which was really surprising also for the, of course, for the data center itself. Or for example, of course, the typical things like the total power consumption over the time. On the job side, we are automatically generating some analytics, some graphs to help the users that are to be a little bit more interested on their application to understand what their applications are doing and to correlate this behavior with the resource in terms of power that they are gathering. For example, just as a final hint, it's very easy also to ask for all the metrics. And for example, this is the visualization of one of the evaluation I was doing by myself. So I was asking the metrics to ER, and I have Grafana locally installed in my laptop, and I was visualizing, for example, the power, the frequency selected, gigaflops. So it was very easy to just load the CSV file that ER was reporting me with one of my commands and visualizing. And just to finalize, ER is, as I said, is open source. So I assume the slides will be shared, so you have here the link. If not, I can share with you. It's a European open source, okay? And the three main topics we are working right now is trying to be more compatible with other tools, support new use cases. In particular, we have in mind to support the more complex use cases like workflow executions, and also new architectures. For example, we are working on porting ER to ARM architectures, okay? And that's all from my side. Thank you very much.
Thank you, Julita.
Thank you, Alan.
We have time for some questions. Any questions from the audience?
Hide behind the, yes, sorry.
Hello.
Yes, actually what I was thinking, something that I don't know whether has been done, is when you're scheduling, I chaired a high-performance computing user group for nearly 20 years, and one of the things with a shared system is fair shares. and the fair share is always based on compute time, or could it be based on energy consumption? And if so, would we be handing down an incentive for the community to try and make their software a little bit more energy efficient, potentially? Yeah, that's if a lot of the scientists that are using HPC are using their own codes, because let's face it, there's always improvements that can be made.
Sorry, but the question was?
The question was, have you looked at energy-aware scheduling then for fair use policy within an HPC?
Energy-aware scheduling is the one that we're using at IBM? Or
No, not necessarily, just a standard PBS-compliant scheduler, batch processing system.
Not at this particular one. We were looking at, for example, at what the one that was used at IBM. And in fact, it was the starting point of our project, let's say.
Okay.
But not at this one. But I will. I
know the Hartree Center in the UK was looking at energy-aware scheduling for the purpose of trying to get a fair share model for their users based on energy consumption. Because based on the title of your presentation, that's why I was going for that as a question. Yeah.
You get more compute time, the less energy you use.
That's
how to
another
incentivize users is also the big question. No? How to not to force, how to involve them in this work.
So does IBM have a tool for that? I haven't seen that.
In low level, they also have a scheduler. It was used at LRZ, in fact, before, I don't know, maybe 6-7 years.
LSF, but I mean that's...
No, LRZ, in the previous data center, the previous system they had before Supercomputing. I mean, the LRZ, Leibniz and Supercomputing center that Laura has mentioned before. Yeah. So they were having a scheduler that was... that was part of the scheduler. I mean, here is completely independent of the scheduler. It's a runtime. The optimization is done in a runtime library, so we are potentially complementary to any optimization at the scheduler level because we are not implemented as a scheduler policy.
Okay, yeah. Okay.
So they have something also that they were trying to do. They were doing, in fact, something very similar, but they were relying on the information they had in the database. So that was the starting point of our project because they realized they cannot use the historical information because the users were probably not voluntarily, but they were cheating the system, no? Because they were doing things like, I will run something very, very efficient at the beginning, and then I will reuse the tags, and they were reusing tags, job names, and things like that just to get accelerated their jobs, no? So we get the same ideas, but we were implementing that runtime with this loop, optimization loop I have mentioned, so there is no way, no easy way the user can cheat the system because it's totally based on the metrics that they are really reporting. So it's not only CPI, there are other metrics because we are not using, for example, utilization, no? Because you can have a very high utilization doing nothing, no? At the end. So that was the motivation or the starting point for our projects, but it's true that I have not looked at the scheduler you mentioned. Thank you.
Time for maybe one more quick question. Okay, I have one. So you were mentioning that you are monitoring, you can interrogate the CPUs and GPUs and measure the power.
Yes.
Do you have enough sensors to really understand, how much the memory is consuming or the processor or the power supply efficiency? Would you like more sensors for you to be able to pull on?
More than sensors, what is missing, in my personal opinion, is more metrics, especially on the GPU side. So on the CPU, I think it has been this effort on providing performance counters. There are many tools you can read with PAPI, with PER, with MSR, with Liquid. There are tools, libraries, there are a lot of things. And the hardware itself is providing a lot of counters that you can get there are some of them really complex to understand, no? But you have a lot of counters.
Counters, okay? Right.
In terms of sensors, you can measure the node power, the RAM. It will be good to be able to measure at the core level, for example, more detail. Okay?
Yeah, more detail.
More detail, it will be good, okay? Yeah. But I think what we have is enough. Because it has been, for a long time, has been very difficult to have access to that. In fact, it's still difficult. It will be better, for example, if we can access at the user level and not need to be root to read that, because that will open the possibility to do much more things. Right. But on the GPU side is what I think it's is really needed to provide
Right.
more information.
Well, I think that goes for all accelerators, because as more accelerators come to the market, it's like
Exactly.
picking and choosing which one you use for an application.
So in here we started reading the typical some values that are available. So in particular with NVIDIA GPUs, like utilization, but utilization in the GPUs means nothing.
Yeah.
I mean,
yeah,
it's just you are
yeah.
using, but we cannot use that. No, so we are now doing efforts in doing something more smart, more intelligent, but it's difficult to correlate the metrics with the application behavior.
Yeah.
No?
And I've also heard a desire to try and get a correlation from those individual component measurements to the wall socket, and actually get, the infrastructure people want to see that.
Yes.
So there's, and this is a big area, being able to monitor the energy, and that's part of the OCP HPC. We want to bring that into our research, into making things more monitorable, to make Julita's life more easy, so she can do more fantastic software. It's great. Thank you very much, Julita.
Thank you.